Hello everyone, welcome to this online course of material characterization organized by NPTEL. We have been looking at the tutorial problems and then I would like to continue the tutorial problems based on the transmission electron microscopy. And yesterday we have seen some of the problems which related to aberrations and its crystallography and so on. In a similar line, we will also try to solve some basic problems which will give you a confidence in solving some of the assignment problems as well as in the problems in the examinations. So, quickly I will go to the board and then start solving this problem. So, the first problem is related to the wavelength of the electrons with increase in the accelerating voltage. So, to calculate the wavelength of the electrons and the radius of the evolved sphere for an operating voltage of 100 kV, 200 kV and then 300 kV in a TEM. So, how to go about it? So, we have the standard formula and then some of the constants are given in the problem for Planck's constant and this is a mass and charge. So, we have the wavelength the relation between the electron volt and the wavelength is this. So, we can simply substitute this constants into this and then we know the evolved sphere radius is 1 by lambda. So, it is now straightforward, we can simply substitute this. Of course, we have to work out this for 3 different voltages, accelerating voltages. So, now we try to do this for 100 kV, your lambda is equal to 6.626 into 10 to the power minus 34 divided by So, for a 100 kilovolt acceleration, you get the lambda 0.00386 nanometers. So, similarly, we can do the simple substitution for the 200 kV. You will be able to get this lambda is equal to 0.00273 nanometers, and for it is 0.00223 nanometers. It changes only the very small in the fourth decimal change, and for calculating the corresponding evolved sphere, it is simple. So, you write R in this case, R is equal to 2.59 into 10 to the power 11 meters. In this case, R is equal to 3.66 into 10 to the power 11 meters. In this case, R is equal to 4.48 . So, the concept you get in this problem is, with the increasing in the acceleration voltage, your lambda keeps decreasing, and once the lambda keep decreasing, the evolved sphere radius will keep on increasing. So, that if you follow the lecture, it clearly shows that why you, in the case of electron microscopes, you have a plenty of diffraction spot occurring on a screen, while in X-ray you have very few diffraction peaks you are able to see in a given spectrum. So, that explains the concept. So, probably you can write one line as the accelerating potential or voltage increases, lambda decreases. So, we can write like that. So, we will move on to second problem. So, the question is find a camera length in a transmission electron microscope with a operating voltage of 120 kV for a material with the d spacing 0.3 nanometers and the radius of diffracting ring is about 10 mm. So, you should recall the lecture notes which talk about a camera length. What is camera length? In a camera length is the distance between the specimen stage and the screen. What is the distance? That is a distance. And then if you recall, there is a relation between a camera length with the diffracted spot spacing. In the case of a polycrystalline pattern, it is a radius of the ring pattern, and in the case of single crystal pattern, it is the distance between the center spot, that is a transmitted spot, with the any one of the diffracted beam R. There is a standard relation. You can use that and then we can solve this problem. So, we will rewrite the wavelength expression first. So, first we find the wavelength lambda similar to the previous problem, then we know the relation L lambda is equal to R d. So, where L is the camera length, so wavelength, this is the distance between the transmitted spot as well as the diffracted spot. So, in the case of a ring pattern, it is a radius of the ring, or in the case of a single crystal spot pattern, it is a distance between any one of the spot and the transmitted beam, and d is our material interplanar spacing. So, we can find the camera length L is equal to R d by lambda, and then you get this by simple substitution. So, you get camera length is around 0.852 meters. So, you see that this relation is a very important relation in the case of solving the diffraction pattern indexing. So, this will be useful. So, the next problem which we are going to talk about is using this relation, how we can solve or index the single crystal electron diffraction pattern. So, we will take up some simple example, and most of the students find it difficult to index them because they have not understood this basic calculation, and then what are the critical things involved in the calculating the distance, or either from the film or it is from the digital photograph. Measuring the distance is a crucial thing, and then how to get the right indexed pattern. So, we will take up some simple exercise for a single crystal diffraction pattern indexing today, and then we will move on to a polycrystal indexing in the next class. Suppose if we take a pattern like this, and which has got the distance 1.10 millimeter in this direction and 0.65 mm this direction. Suppose if you have this kind of a pattern, and how to proceed further. What you should understand here is there are 2-3 methods possible. What I am going to demonstrate today is the ratio method. This especially used when there is no symmetry of the pattern is known. For example, if you do not know the symmetry, for example, at least I can identify this is a rectangular pattern or a square pattern or a hexagonal pattern and so on. If you are not able to recognize the pattern, for example, this is not exactly I would say a symmetry is known or something like that, but this method is used also when the camera constant is not known, or sorry, camera constant is known. So, excuse me, camera constant is known, then this method is preferably used, but nevertheless we will not take those into consideration. We will assume that we do not know any data on those parameters. So, how to go about it? So, when you look at the pattern like this in a film or from the digital recording media, and if you always you see that the center spot is a transmitted beam, it started with 0, 0, 0, Okay. So, from there how to proceed? So, let us write down some procedures. Suppose if we assume that this is from an FCC crystal, let us look at how to proceed. First we seek the ratios of h square plus k square plus L square from the of an FCC crystal. So, first what you have to do this, the first step is to we seek the ratios of square root of h square plus k square plus L square from the allowed HKL of an FCC crystal, and these ratios are equal to the ratios of spot separations in the diffraction pattern. So, that means the ratios of this distance, these two distance will be equivalent to the ratios of some of the allowed this HKL indices ratios. So, we need to list. So, first list the allowed, first make a list of these ratios in table. So, we will make a table now. So, what we have done now is we have generated a table. What are these indices? These are all allowed FCC HKL. So, we have done that square root of h square k square plus L squared like this, and this is relative spacings. This to be compared. Now, the next step is what we will do. First, we have to look at this. I will write down the procedure, so that this is the procedures. So, I will write this as procedure number 4. Now, look for diffractions in table So, the fourth procedure is, now look for diffractions in the table, preferably low order ones. That means, you should not look at these things. Initially, you should look at low order reflections, and whose spot spacings are in ratio of the measured distance from the diffraction pattern. So, we have now the distance here, what we have given, this distance and this distance. So, we will take that into that ratio, and then we will see what we get. So, what is the ratio? 0.65 divided by 1.10, which is equal to 0.591. And we can find trial and error, that square root of 3 by square root of 8 is equal to 0.61. So, this ratio corresponds to So, the next is, we can find the trial and error, that square root of 3 by square root of 8 is 0.61, and this ratio corresponds to 111 and 220 diffractions, which seems to be promising to work further on this before we finally zero in on this indices. This at least looks promising. So, what is the next step? Note the diffraction pair two zero zero and 311 the pair 200 and 222 and the pair 220 and 422. Also have similar ratios of their spot spacing. So, if we go with this rule and the other diffraction pair like 200 and 311 and the other pair 200 and 222, the other pair 220 and 422 also have similar ratios of their spot spacings. So, how to decide that these two are the only one which is going to be correct, which one is correct. So, now we have to choose the other set of rules, which is point number 7. We need specific vectors in the 2 families that provide the correct angles in the So, the next step is we need to choose a specific vectors in the 111 and 220 families that provide the correct angles in the diffraction pattern. So, if you look at the pattern, it has got about these two indices have the some angle. So, we will redraw that. Here we use So, the next important thing one we need to look at it, since we have to take two vectors from these two families, we have chosen these two, though others also will work, but the condition is you have to have this dot product should be 0. That means these two vectors are perpendicular to each other. That is what we have seen in the initial spot. We are trying to solve that spot. I will redraw them once we go to the next step. So, that means this is consistent with these spots are consistent with the observed 90-degree angles. So, with this condition we can eliminate the other possible vectors. For example, those vectors, all these vectors we can eliminate, the other possible pairs we can eliminate, because no vectors in their families are at 90 degrees angles. So, now we can since none of these pairs have the angles between them of 90 degree, with the initial inspection we can now try to complete that diffraction pattern. So, this is 0 0 0 and we will take two vectors, one is this, one is that. Let us label this as 1 1 1 and this is 2 2 0, because these two vectors are at 90 degrees. So, at 90 degrees. So, that is what we have found out from this relation, and then now we can fill up this, because other spots are the linear combination of these two vectors. We can do that, and this is the zone axis is obtained from the vector product. That is 2 2 0 into is equal to 2 minus 0 x plus 0 minus 2 y plus 2 plus 2 z is equal to 2, 2, 4, parallel 1, 1, 2. So, the cross product of these two vectors gives this, and then which is nothing but a parallel to this plane 1 bar 1 2. So, that is how the zone axis is calculated. So, we will solve a similar problem, maybe one or two more, to get more familiarity with this indexing. And this is a manual indexing. Today you have the software available, but and of course what we are now trying to solve is a very simple cubic system. And if you go to the much more less symmetric system, then these calculations will become much more tedious, and that is where you require a computer program to do this. And today we have all the softwares available, but nevertheless you should know what is the calculation behind all the software, and that is the primary aim of this exercise. You should know, you should try with some of the basic things, and we will solve some few more exercises like this for a cubic system as well as for the polycrystalline system in another tutorial class. So, with that I will stop this tutorial class, and then I will try to continue in the next class. Thank you.